At the end of this video, you should be able to write a word equation and a formula equation for a given chemical reaction, and balance a formula equation by inspection. The first step in writing a chemical equation is to identify the facts to be represented. It is often helpful to write a word equation, which is an equation in which the reactants and products in a given chemical reaction are represented by words. A word equation has only qualitative, meaning descriptive, meaning. It does not give the whole story because it does not give the quantities of the reactants used or products formed. Consider the reaction of methane, which is the principal component of natural gas, reacting with oxygen. When methane burns in air, it combines with oxygen to produce carbon dioxide and water vapor. In the reaction, methane and oxygen are the reactants, and carbon dioxide and water are the products. The word equation for the reaction of methane and oxygen is written on the screen here. The arrow is read as react to yield or yield. Also, they can be read as produces or forms. So the equation on the screen is red. Methane and oxygen react to yield carbon dioxide and water. Or simply, methane and oxygen yield carbon dioxide and water. The next step in writing a correct chemical equation is to replace the names of the reactants and products with appropriate symbols and formulas. Methane is a molecular compound composed of one carbon atom and four hydrogen atoms. Its chemical formula is CH4. Recall that oxygen exists in nature as diatomic molecules. It is therefore represented as O2. The correct formulas for carbon dioxide and water are CO2 and H2O, respectively. A formula equation represents the reactants and products of a chemical reaction by their symbols or formulas. The formula equation for the reaction of methane and oxygen is written on the screen here. The G in parentheses after each formula indicates that the corresponding substance is in the gaseous state. Like a word equation, a formula equation is a qualitative statement. It gives no information about the amounts of reactants or products. To complete the process of writing a correct equation, the law of conservation of mass must be taken into account. The relative amounts of reactants and products represented in the equation must be adjusted so that the numbers and types of atoms are the same on both sides of the equation. This process is called balancing an equation and is carried out by inserting coefficients. Once it is balanced, a formula equation is a correctly written chemical equation. Look again at the formula equation for the reaction of methane and oxygen. To balance the equation, begin by counting atoms of elements that are combined with atoms of other elements and that appear only once on each side of the equation. In this case, we could begin by counting either carbon or hydrogen atoms. Usually, the elements hydrogen and oxygen are balanced only after balancing all other elements in an equation. Thus, let's begin by counting carbon atoms. Inspecting the formula equation reveals that there is one carbon atom on each side of the arrow. Therefore, carbon is already balanced in the equation. Counting hydrogen atoms reveals that there are 4 hydrogen atoms in the reactants, but only 2 in the products. 2 additional hydrogen atoms are needed on the right side of the equation. They can be added by placing the coefficient 2 in front of the chemical formula H2O. A coefficient multiplies the number of atoms of each element indicated in a chemical formula. Thus, 2H2O represents 4 hydrogen atoms and 2 oxygen atoms. To add 2 more hydrogen atoms to the right side of the equation, one may be tempted to change the subscript in the formula of water so that H2O becomes H4O. However, this would be a mistake because changing the subscripts of a chemical formula changes the identity of the compound. H4O is not a product in the combustion of methane. In fact, there is no such compound. One must only use coefficients to change the relative number of atoms in a chemical equation because coefficients change the numbers of atoms without changing the identities of the reactants and products. Now consider the number of oxygen atoms. There are 4 oxygen atoms on the right side of the arrow in the partially balanced equation. Yet, there are only 2 oxygen atoms on the left side of the arrow. One can increase the number of oxygen atoms on the left side to 4 by placing the coefficient 2 in front of the molecular formula for oxygen. This results in a correct chemical equation, or balanced formula equation, for the burning of methane in oxygen. This reaction is further illustrated on the figure on the screen here. In a Bunsen burner, methane combines with oxygen in the air to form carbon dioxide and water vapor. This reaction is represented by both a molecular model and a balanced equation. Each shows that the number of atoms of each element in the reactants equals the number of atoms of each element in the products. The table on your screen here summarizes the symbols commonly used in chemical equations. Sometimes a gaseous product is indicated by an arrow pointing upward instead of G. A downward arrow is often used to show the formation of a precipitate during a reaction in solution. The conditions under which a reaction takes place are often indicated by placing information above or below the reaction arrow. The word heat, symbolized by a Greek capital delta, indicates that the reactants must be heated. The specific temperature at which a reaction occurs may also be written over the arrow. For some reactions, it is important to specify the pressure at which the reaction occurs, or to specify that the pressure must be above normal. Many reactions are speeded up and can take place at lower temperatures in the presence of a catalyst. A catalyst is a substance that changes the rate of a chemical reaction, but can be recovered unchanged. To show that a catalyst is present, the formula for the catalyst, or the word catalyst, is written over the reaction arrow. In many reactions, as soon as the products begin to form, they immediately begin to react with each other and reform the reactants. In other words, the reverse reaction also occurs. The reverse reaction may occur to a greater or lesser degree than the original reaction, depending on the specific reaction and the conditions. A reversible reaction is a chemical reaction in which the products reform the original reactants. The reversibility of a reaction is indicated by writing 2 arrows pointing in opposite directions. For example, the reversible reaction between iron and water vapor is a common example. With the understanding of all the symbols and formulas used, it is possible to translate a chemical equation into a sentence. So, again, consider the following equation, translated into a sentence. When heated, solid mercury 2 oxide yields liquid mercury and gaseous oxygen. It is also possible to write a chemical equation from a sentence describing a reaction. Consider the sentence, under pressure and in the presence of a platinum catalyst, gaseous ethene and hydrogen form gaseous ethane. This sentence can then be translated into an equation. Throughout this chapter, we will often include the symbols for physical states, meaning S, L, G, and AQ, in balanced formula equations. You should be able to interpret these symbols when they are used and to supply them when the necessary information is available. Chemical equations are very useful in doing quantitative chemical work. The arrow in a balanced chemical equation is like an equal sign, and the chemical equation as a whole is similar to an algebraic equation in that it expresses an equality. Let's examine some of the quantitative information revealed by a chemical equation. 1. The coefficients of a chemical reaction indicate relative, not absolute, amounts of reactants and products. A chemical equation usually shows the smallest numbers of atoms, molecules, or ions that will satisfy the law of conservation of mass in a given chemical reaction. Consider the equation for the formation of hydrogen chloride from hydrogen and chlorine. on the screen here. The equation indicates that 1 molecule of hydrogen reacts with 1 molecule of chlorine to produce 2 molecules of hydrogen chloride, giving the following molecular ratio of 1 molecule of H2 to 1 molecule of Cl2 to 2 molecules of HCl. This ratio, 1 to 1 to 2, this ratio shows the smallest possible relative amounts of the reaction's reactants and products. To obtain larger relative amounts, we simply multiply each coefficient by the same number. Thus, 20 molecules of hydrogen would react with 20 molecules of chlorine to yield 40 molecules of hydrogen chloride. The reaction can also be considered in terms of amounts in moles. 1 mole of hydrogen molecules reacts with 1 mole of chlorine molecules to yield 2 moles of hydrogen chloride molecules. 2. The relative masses of the reactants and products of a chemical reaction can be determined from the reaction's coefficients. Recall that the amount of an element or compound in moles can be converted to a mass in grams by multiplying by the appropriate molar mass. We know that 1 mole of hydrogen reacts with 1 mole of chlorine to yield 2 moles of hydrogen chloride. The relative masses of the reactants and products are calculated as is shown on the screen here. The chemical equation shows that 2.02 grams of hydrogen will react with 70.90 grams of chlorine to yield 72.92 grams of hydrogen chloride. 3. The reverse reaction for a chemical equation has the same relative amounts of substances as the forward reaction. Because a chemical equation is like an algebraic equation, the equality can be read in either direction. Reading the hydrogen chloride formation equation mentioned on the previous slide and on the screen here, reading it from right to left, we can see that 2 molecules of hydrogen chloride break down to form 1 molecule of hydrogen plus 1 molecule of chlorine. Similarly, 2 moles of hydrogen chloride, which would be 72.92 grams, yield 1 mole of hydrogen, which is 2.02 grams, and 1 mole of chlorine, 70.90 grams. We have seen that a chemical equation provides useful quantitative information about a chemical reaction. However, there is also important information that is not provided by a chemical equation. For instance, an equation gives no indication of whether a reaction will actually occur. A chemical equation can be written for a reaction that may not even take place. Some guidelines about the types of simple reactions that can be expected to occur are given in the next sections. And later chapters provide additional guidelines for other types of reactions. In all these guidelines, it is important to remember that experimentation forms the basis for confirming that a particular chemical reaction will occur. In addition, chemical equations give no information about the speed at which reactions occur or about how the bonding between atoms or ions changes during the reactions.
The coefficients in a chemical reaction describe how much of one reagent is consumed relative to another. For example, 1 molecule of methane burns with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. To burn 3 molecules of methane would require 6 molecules of oxygen. Burning 2 moles of methane, we would produce 4 moles of water. The coefficients indicate the relative amounts of reactants and products. Because coefficients indicate the relative number of moles, and since the mass of 1 mole of each of the substances can be calculated, 16 grams of methane will react with 64 grams of oxygen to produce 36 grams of water. Furthermore, the mass relationships between reactants and products apply even if the reaction is reversed.
Most of the equations in the remainder of this chapter can be balanced by inspection. The following procedure demonstrates how to master balancing equations by inspection using a step-by-step approach. The equation for the decomposition of water will be used as an example. Step 1. Identify the names of the reactants and the products, and write a word equation. The word equation for the decomposition of water is written on the screen now. Step 2. Write a formula equation by substituting correct formulas for the names of the reactants and products. We know that the formula for water is H2O, and recall that both hydrogen and oxygen exist as diatomic molecules. Therefore, their correct formulas are H2 and O2 respectively. Step 3. Balance the formula equation according to the law of conservation of mass. This last step is done by trial and error. Coefficients are changed and the numbers of atoms are counted on both sides of the equations. When the numbers of each type of atom are the same on both sides of the products, both the products and the reactants, the equation is balanced. The trial and error method of balancing equations is made easier by the use of the following guidelines. Balance the different types of atoms one at a time. First, balance the atoms of elements that are combined and that appear only once on each side of the equation. Balance polyatomic ions that appear on both sides of the equation as single units. And lastly, balance hydrogen atoms and oxygen atoms after atoms of all other elements have been balanced. The formula equation in our example shows that there are 2 oxygen atoms on the right and only 1 on the left. To balance oxygen atoms, the number of H2O molecules must be increased. Placing the coefficient 2 before H2O gives the necessary 2 oxygen atoms on the left. The coefficient 2 in front of H2O has upset the balance of hydrogen atoms, however. Placing the coefficient 2 in front of hydrogen, H2, on the right gives an equal number of hydrogen atoms, which is 4, on both sides of the equation. Step 4. Count all atoms to be sure that the equation is balanced. Make sure that equal numbers of atoms of each element appear on both sides of the arrow. Occasionally at this point, the coefficients do not represent the smallest possible whole number ratio of reactants and products. When this happens, the coefficients should be divided by their greatest common factor in order to obtain the smallest possible whole number coefficients. Balancing chemical equations by inspection becomes easier as you gain experience. Learn to avoid the most common mistakes, like writing incorrect chemical formulas for reactants or products, and trying to balance an equation by changing subscripts. Remember that subscripts cannot be added, deleted, or changed. Eventually, you will probably be able to skip writing the word equation and each separate step. However, do not leave out the final step of counting atoms to be sure that the equation is balanced.
Balancing a chemical equation is an important technique to help you understand the chemical reaction thoroughly. The first step is to identify the reactants and products. In this example, the reactants are aluminum carbide and water. The products are aluminum hydroxide and methane. Next, write a word equation showing the change of reactants to products. Remember to specify if your reagents and reactants are solid, liquid, or gas. Now, convert the word equation to a chemical equation with chemical formulas. Now balance atoms one reaction at a time by matching the coefficient times the subscript on the left side of the reaction to the coefficient times the subscript on the right side of the equation for each element. Start with elements that are only in one reactant or product. In this example, the 4 aluminums in one molecule of aluminum carbide lead to 4 molecules of aluminum hydroxide. The 3 carbon atoms in one molecule of aluminum carbide on the reactant side lead to 3 carbon atoms in the molecules of methane on the product side. Next, the 12 atoms of oxygen in 4 molecules of aluminum hydroxide on the product side cause us to make sure there are also 12 atoms of oxygen in the molecules of water on the reactant side. Looking at hydrogen, the 4 molecules of aluminum hydroxide on the product side contain 12 atoms of hydrogen, and the 3 molecules of methane contain 12 atoms of hydrogen. This gives us a total of 24 atoms of hydrogen on the product side. This is the same number of atoms of hydrogen as found in 12 molecules of water on the reactant side, so our equation is balanced. We double-check to make sure the coefficients have been reduced to the smallest number possible. In cases where you have polyatomic ions, you can balance the ions as whole units if they appear on both sides of the equation. Always be sure to make sure the charges balance.
At this point, you should be able to write a word equation and a formula equation for a given chemical reaction, as well as balance a formula equation by inspection.